Hello students, welcome back to online entrance examination classes. Today we solve some problems. Okay, the first question: for photoelectric emission, tungsten requires light of 2300 angstrom. If light of 1800 angstrom wavelength is incident, then emission, four options are given. First one, takes place; B, does not take place; C, may or may not take place; and D, depends on frequency. Okay, how to solve this particular problem? See, read properly the problem. For photoelectric emission, tungsten requires light of 2300 angstrom. So given is the threshold wavelength. So threshold wavelength is given. If light of 1800 angstrom wavelength is incident, then what happens to emission, whether it is taking place or not, or depends on frequency, or may not take place. Okay, so threshold wavelength is given. So lambda max is equal to 2300 angstrom. Angstrom is 10⁻⁻10 meter. Okay, so now the incident photons or light have the wavelength 1800 angstrom, right? So which is less than the threshold wavelength. So what is the definition of threshold wavelength? It is the maximum wavelength above which photoelectric emission does not take place, right? So now the incident wavelength is 1800 angstrom, which is lesser than the threshold wavelength. No doubt the photoelectric emission does take place because wavelength is less than the threshold wavelength, right? There is a maximum limit for the wavelength, but there is no minimum value. Okay, whatever may be the value within this particular value, so photoelectric emission takes place. So therefore the option is A, takes place. Okay, in case of frequency, if instead of wavelength, if frequency is given, say threshold frequency is given, and if the incident light has the frequency which is less than the threshold frequency, then photoelectric emission does not take place. But here it is given the wavelength which is less than threshold wavelength, so photoelectric emission takes place. Okay, so we move on to the next question. So according to photoelectric equation, the graph between the kinetic energy of photoelectrons ejected and the frequency of incident radiation is. Four options are given, four graphs are given, A, B, C, D. All the graphs tells about the variation of kinetic energy of emitted photoelectrons, maximum value of kinetic energy of emitted photoelectrons with respect to the frequency. Okay, see these four graphs. See, in the first graph, as soon as the incident frequency is increased, I mean the frequency of incident photons are increased, the kinetic energy of emitted photoelectrons goes on decreasing. Okay, which is not possible because kinetic energy of emitted photoelectrons depends on the frequency of incident radiation, frequency of incident photons, right? So here it is proportional to the frequency. Okay, kinetic energy of emitted photoelectrons are dependent on the frequency, means if you increase the frequency, kinetic energy of emitted photoelectrons increases. Okay, here it is decreasing, therefore this is not the correct option. What about this option? See, when the frequency is 0, there are certain electrons which are emitted by the photosensitive material with a certain amount of kinetic energy, which is not possible without any incident photon. No. So this option is wrong. So what about the third option? See, when the frequency is 0, there are no the kinetic energy of emitted photoelectrons is 0. As soon as the frequency is increased from 0, then kinetic energy goes on increasing. Means what? So as soon as you increase the frequency from 0 of incident photons, there is emission of photoelectrons with certain amount of kinetic energy, which violates the definition of threshold frequency, right? So there is a minimum frequency for the material above which photoelectric emission does take place. Okay, so therefore the correct option is 4, right? So if you go on increasing the frequency from 0, after the threshold frequency, the kinetic energy of emitted photoelectrons is directly proportional to the frequency of incident photons. The correct option is 4, D. Okay, so next question. The work function of a substance is 4 electron volt. The longest wavelength of light that can cause photoelectron emission from this substance is approximately. Okay, so work function is given. Okay, what is work function? Is a minimum energy needed for the photon. Minimum energy of photons are required to eject the electrons, right, to produce a photoelectric effect. Okay, the work function is given. Work function of the substance is 4 electron volt. It will be phi naught. The work function is phi naught. It is 4 electron volt. The longest wavelength of light that can cause photoelectron emission from this substance. What do you mean by the longest wavelength? So they are speaking about what is called the threshold wavelength. Okay, it is the longest wavelength. What is the threshold wavelength of light that can cause photoelectron emission? Okay, work function is given 4 electron volt. So how do you calculate the longest wavelength? Okay, you know phi naught is equal to h into nu, right? So this is equal to h c by lambda. See, if you substitute the values for h and c, h is Planck's constant 6.625 × 10⁻³ Joule/second, c is velocity of light in vacuum, that is 3 × 10⁸ meter/second. If you substitute the values for h and c, and if you express lambda in terms of angstrom, then the energy in terms of electron volt will be this much. So 12,400 divided by lambda, which is in terms of angstrom, that much of electron volt. If you substitute all the values, you will get in terms of joules. Okay, so to convert it into electron volt, you have to divide it by 1.6 × 10⁻⁹. Okay, so then so here we expressed the energy in terms of electron volt. Okay, so remember this particular expression. Okay, right, it may be phi naught work function or energy of photon, whatever. Okay, so 12,400 by lambda, that much of electron volt. Here the work function is given, it is 4 electron volt. Okay, you have to calculate the value of lambda. Okay, so if I calculate this by 4, so therefore lambda maximum is equal to, so 3100 angstrom, 3100 angstrom, Okay, as I told, lambda in terms of angstrom, that is 10 to the power of minus 10 meter. Okay, so the correct option is C, 310 nanometer, because this is 3100 10 to the power of minus 10 meter. If expressed in terms of nano means 10 to the power of minus 9. This is 310 10 to the power of minus 9 meter. It is 310 nanometer. So the correct option is C. Okay. So we move on to next question. The anode voltage of a photocell is kept fixed. The wavelength of light falling on the cathode is gradually changed. The plate current I of the photocell varies as follows. What happens to the plate current flowing? What happens to the current flow if you change the wavelength? Which one is the correct option? Okay, see, in this, if you can compare the four graphs, see here all the graphs tells about the variation of current with respect to lambda. See here, if I consider this point is a threshold wavelength. Threshold wavelength is the wavelength below which photoelectric emission does take place, above which photoelectric emission does not take place. Here what happens? See, current is increasing continuously and reaches the maximum value and it is decreasing, which is not possible. So what about this graph? See this also, say if this is lambda maximum threshold wavelength, above the threshold wavelength current is increasing, which is not possible. Here there is no threshold wavelength at all. Okay, if you increase the wavelength of incident radiation from 0, current increases, which is not possible. The correct option is D, right? See, initially current is maximum, and if you increase the wavelength of incident photons, current gradually decreases and becomes 0. Why? See, if I consider the Einstein's photoelectric equation, the maximum value of kinetic energy of emitted photoelectrons is given by K maximum, which is equal to hc by lambda minus phi naught. Phi naught is a work function and it is constant for that particular photosensitive material. Okay, if you increase the value of lambda, what happens to the maximum value of kinetic energy of emitted photoelectrons? It goes on decreasing. See, in the apparatus you have this is emitter plate, means cathode, this is collector plate, anode, electrons emitted by the emitter plate, right? There is collector plate. If you decrease the kinetic energy of emitted photoelectrons by increasing the wavelength of incident photons, then a lesser and lesser number of electrons will reach the collector plate, thereby current decreases. Okay, on increasing the value of lambda, the wavelength of incident photons, so kinetic energy decreases. If kinetic energy is decreasing, lesser and lesser number of electrons will reach the collector plate. Okay, I am not speaking about now. See, if you change the wavelength, whether the saturation current changes? No, you are fixing the value of anode voltage. You are not changing the value of anode voltage. It is fixed. You are increasing the value of lambda. right? See, once the saturation current is reached and if you increase the value of lambda, photoelectric current doesn't change, okay, until threshold wavelength reaches. Once the threshold wavelength is reached, above the threshold wavelength, photoelectric emission does not take place, right? Okay, so at any intermediate stage, you are fixing the value of anode voltage and you are increasing the value of lambda. So naturally, you are decreasing the kinetic energy of emitted photoelectrons. So therefore, less number of electrons will reach the collector plate, that reduces the current. Current goes on decreasing, okay, decreasing until lambda becomes lambda maximum. Okay, once the threshold wavelength is reached, current becomes 0. The correct option is D. Okay, the next question, question number 5. When photons of energy h nu fall on an aluminum plate of work function omega naught, the photoelectrons of maximum kinetic energy K are ejected. If the frequency of radiation is doubled, the maximum kinetic energy of the ejected photoelectron will be. Okay, in this particular problem, energy of incident photon is given, that is h nu, and work function is given, it is omega naught. What about the maximum kinetic energy of photoelectrons? It is K. If the frequency of radiation is doubled, you are not changing the intensity, only you are changing the frequency, and you are making the frequency double the initial value, twice the initial value. The frequency of radiation is doubled. The maximum kinetic energy of the ejected photoelectron will be. See the options, 4 options. First option is K plus h nu. K is the initial value of maximum kinetic energy of emitted photoelectrons. As you know, the electrons emitted from the surface of the photosensitive material, they have the greater value of kinetic energy, right? Okay, if the frequency of radiation is doubled, the maximum kinetic energy of the ejected photoelectrons, let it be K dash, which is equal to, in terms of initial value of kinetic energy and the energy of incident photon, the first option is given K plus h nu. Option B, K plus omega naught, in terms of initial value of maximum value of kinetic energy and the work function. Okay, C, twice of the initial value, 2K, and fourth option is K, that remains the same, maximum value of kinetic energy is not changing. So which option is correct? Okay, so we use Einstein's photoelectric equation to solve this particular problem. Okay, so we have K maximum is equal to h nu minus phi naught. Okay, h nu is the energy of incident photon, phi naught is the work function. K maximum is the maximum value of kinetic energy of emitted photoelectron. For the first case, kinetic energy is given, it is K, and incident photon is h nu, work function is omega naught. For the second case, what is the new value of maximum value of kinetic energy of emitted photoelectrons? If the frequency of radiation is doubled, nu, initial value is nu, now this is 2 times, here it is 2 times nu, twice the initial value, so therefore 2h nu minus omega naught. So this is equal to h nu plus h nu minus omega naught. But what is h nu minus omega naught? It is equal to K, therefore this is equal to h nu plus K. This is the new value of the maximum value of kinetic energy of emitted photoelectrons if the frequency is made twice the initial value. Okay, right. So the correct option is S1, K plus h nu. So move on to next question. Question number 6. An electron is accelerated through a potential difference of 200 volts. If E by m for the electron is 1.6 into 10 to the power of 11 coulomb per kg, the velocity acquired by the electron will be. What do you mean by E by m ratio? If you calculate the charge to mass ratio, it is called the specific charge of that particular particle. So given the specific charge of electron, E by m, that is equal to 1.6 into 10 to the power of 11 coulomb per kg. The specific charge is given, okay, 1.6 into 10 to the power of 11 coulomb per kg. What is the velocity of the electron? What is the velocity acquired by the electron? Okay, if that electron is accelerated through a potential difference of 200 volt. See, we studied the kinetic energy gained by the electron or any charged particle. If it is accelerated through a potential difference of V, is the charge times the potential difference applied. This is the kinetic energy gained by any charged particle if that particular charged particle is accelerated through a potential difference of V. For the electron, you can write it is E into V. Okay, using this value, that is specific charge of the electron, you have to calculate what is the maximum value of velocity acquired by the electron if it is accelerated through a potential difference of 200 volt. Okay, so we want the value of V maximum. So V maximum square is equal to 2 times E into V divided by m. So this is equal to 2 into E by m into V. Right? Okay, so therefore V maximum square is equal to 2 into the specific charge of the electron is given, so 1.6 into 10 to the power of 11. The potential difference is 200 volts. So this is equal to, see, this is 16 into 10 to the power of 10. Okay, so into 2 into 2 is 64. This is 10 to the power of if this is 10 to the power of 10, this is 10 into 2 to the power of 12. V maximum square, right? If this is 16, then 16 into 10 to the power of 10. Okay, 16 into 2 into 2, there is 64 into, here it is 10 to the power of 10 into 10 to the power of 2, 10 to the power of 12. Now you can take the square root, right? So express this power in even number. Okay, so V maximum is equal to therefore square root of 64 into 10 to the power of 12. So therefore this is equal to 8 into 10 to the power of 6 meter per second. Okay, the option is D. Okay, so remember E by m is called the specific charge, or in general Q by m. Q is the charge of any charged particle and m is the mass of that particular charged particle. If you take the ratio of charge of that particular charged particle to its mass, you are calculating what is called the specific charge. Okay, so this is the maximum value of velocity acquired by the electron. Okay. Okay, so the next question, question number 7. The specific charge of a proton is 9.6 into 10 to the power of 7 coulomb per kg. The specific charge of an alpha particle will be, see, as I told, what is specific charge? Specific charge is nothing but charge to mass ratio. The specific charge of a proton is given, that is 9.6 into 10 to the power of 7 coulomb per kg. What is the specific charge of an alpha particle? What do you mean by an alpha particle? What is that alpha particle? It is helium nucleus. Helium nucleus is called alpha particle, which has 2 protons and 2 neutrons. Atomic number is 2 and mass number is 4. Okay, so you are given with the specific charge of proton, it is given. What is the specific charge of an alpha particle? You have to calculate. Okay, so how to solve this problem? The specific charge of proton, say charge of the proton is Qp, the mass of proton is Mp, Qp by Mp, it is equal to, it is given 9.6 into 10 to the power of 7 coulomb per kg. What is the specific charge of an alpha particle? Say Q alpha by M alpha is equal to how much? Okay, so how to calculate? You have to compare the charge of the alpha particle with the charge of proton. I mean, what about the charge of the alpha particle if it is consisting of 2 protons? And what about its mass? Okay, see, it has 2 protons, therefore for the alpha particle, Q alpha is 2 times the charge of the proton, right? Its charge is now 2 into Qp, where Qp is the charge of the proton. Now it has 2 protons, therefore twice the charge of proton. So divided by M alpha. What about mass? It is nearly 4 times the mass of proton. It has 2 protons and 2 neutrons. Mass of proton and mass of neutron, they are not equal, they are nearly equal. So therefore approximately, since it has its atomic number is 4, there are 2 protons, 2 neutrons, or in general 4 nucleons. Since it has 4 nucleons, the mass of alpha particle is nearly 4 times the mass of proton, right? Okay, so therefore this is equal to half of Qp by Mp. Okay, so mass of alpha particle is nearly 4 times the mass of proton. Okay, this is equal to half into Qp by Mp, it is given, so 9.6 into 10 to the power of 7 coulomb per kg. So this is equal to 4.8 into 10 to the power 7 coulomb per kg. The correct option is option B, 4.8 into 10 to the power of 7 coulomb per kg. Okay, we move on to the next question. So threshold wavelength for a metal is 5200 angstrom. So that wavelength comes in visible region, right? Photoelectrons will be ejected if it is irradiated by a light from 50 watt infrared lamp, 1 watt infrared lamp, 20 watt ultraviolet lamp and 0.5 watt infrared lamp. See, different sources are given. I mean, there are 2 sources. One is, one source emitting infrared rays, the other source emitting ultraviolet rays, right? But different powers. See here 50 watt infrared lamp, 1 watt infrared lamp, 20 watt, here 0.5 watt. See in these three options all are infrared, they are infrared lamp. The source is emitting infrared rays. In this particular option, the source is emitting ultraviolet rays. So that particular wavelength comes in visible region. See, given the threshold wavelength for a metal is 5200 angstrom, that is maximum value of wavelength for a metal is given. It is 5200 angstrom, which comes in visible region, right? So photoelectrons will be ejected if it is irradiated by a light from. Don't see these power values, okay, right? See, this is ultraviolet lamp and these three are emitting infrared rays. See, what about the wavelength? So how the wavelength varies? How does the wavelength vary from radio waves to gamma rays? Okay, a red man in violet uniform with the X gun. So the frequency is increasing in this particular direction, whereas wavelength is decreasing in this particular direction. Okay, this is radio waves, microwaves, infrared rays, so visible light, ultraviolet rays, X-rays, gamma rays. A red man in violet uniform with the X gun. A Shaktiman illidda hage. A red man in violet uniform with the X gun. Corona annu hogaladislikke bandava. Okay, so if you see the wavelength range, see wavelength of ultraviolet rays is less than the visible light, right? As I told, from right to left, okay, sorry, left to right, the wavelength is decreasing, right? What about the wavelength of infrared rays? It is greater, okay, compared to this. This is lesser compared to this. What about the threshold wavelength? What is the definition of threshold wavelength? It is a maximum wavelength above which photoelectric emission does not take place. It is a maximum wavelength. This wavelength comes in visible region. This is a maximum wavelength for that particular metal, above which wavelength is increasing, right? Frequency is increasing this particular direction, wavelength is increasing this particular direction, right? So this is the maximum wavelength which comes in visible region now for that particular metal, above which photoelectric emission does not take place. Below definitely photo emission takes place. So therefore, if that metal is irradiated with the ultraviolet rays, whatever may be the power of source used, that metal definitely emit photoelectrons. So the correct option is option C, 20 watt ultraviolet lamp. Okay, the option is C. See the other three options: infrared, infrared, infrared. The wavelength is here greater than the threshold wavelength. Therefore, the correct option is this one. For ultraviolet lamp, that metal does emit the photoelectrons. Okay, next question. So light of two different frequencies whose photons have energies of 1 electron volt and 2.5 electron volt respectively illuminate successively a metal having work function 0.5 electron volt. The ratio of maximum speed of emitted photoelectrons is. See, given light of two different frequencies whose photons have energies 1 electron volt and 2.5 electron volt respectively, illuminate successively a metal one after the other having work function. What is the work function of the metal? It is 0.5 electron volt. What are the energies of incident photons? 1 electron volt and 2.5 electron volt. You know the energy dependent on the frequency. Okay. Photons have the energies of 1 electron volt and 2.5 electron volt. The work function is given. Work function of the metal is 0.5 electron volt. What is the ratio of maximum speed of emitted electrons? Okay, so photons have energies of 1 electron volt and 2.5 electron volt respectively. Illuminate successively one after the other a metal having work function 0.5 electron volt. Work function is given, it is 0.5 electron volt. Okay, the photons have energies 1 electron volt and 2.5 electron volt. What is the ratio of maximum speed of emitted electrons? See, for the first case, see, we have K maximum is equal to h nu minus phi naught, right? Einstein's photoelectric equation. For the first case, if I write, is half maximum square is equal to h nu minus phi naught. This is equal to h nu. The energy of incident photon is given. This is 1 electron volt. The work function is 0.5 electron volt. This is equal to 0.5 electron volt. And for the second case, the kinetic energy of maximum value of kinetic energy of emitted photoelectrons, say half m b dash square, is equal to h nu dash minus phi naught. Work function remains the same. It is dependent on the metal. Okay, so therefore this is equal to h nu dash. The photons have energies 1 electron volt and 2.5 electron volt. For the second case, the photon has the energy 2.5 electron volt. Work function is 0.5 electron volt. This is equal to 2 electron volt. What is asked? The ratio of maximum speed of emitted electrons. You have to calculate the ratio V maximum to V maximum dash. So, if you divide these two, what you will get? Divide equation 1 by 2, so half m is getting cancelled, so V maximum square by V maximum dash square, that is equal to 0.5 by 2, this is equal to 1 by 4, right? 0.5 is half into half, this is 1 by 4. So therefore square root of this V maximum by V maximum dash, that is equal to 1 by 2. Therefore the velocities are in the ratio 1:2. The correct option is A. Okay, the correct option is A, 1:2. The maximum value of velocities are in the ratio 1:2. The correct option is A.